Hello, in this lecture we will find the area of a circle. In the drawing we have a circle and inside the circle we have a shape. This angle ADC is a right angle, it equals to 90 degrees, and also angle BCD equals to 90 degrees, and the side AD of this shape equals to 4 units, and the side DC of this shape equals to 6 units, and side BC of this shape equals to 8 units, and we want to find out the area of this circle. Okay, first of all I will explain what are one-sided angles. Okay, actually when you have line A and this is line A, and also line B, this is line B, and line C intersects with those two lines, this is line C, that intersects with line A at this point, and line C intersects with line B at this point. Actually, angles alpha and beta are defined as one-sided interior angles. So I will write it down. Angles alpha and beta are defined as one-sided internal angles. Okay, angles alpha and beta are defined as one-sided internal angles. One-sided interior angles. Again, angles alpha and beta defined as one-sided interior angles. First of all, why angles alpha and beta are one-sided angles? The reason for that is that actually angles alpha and beta located on the same side of line C. Okay, so in relation to line C, angles alpha and beta are located on the same side. Actually, we can say that angles alpha and beta are located, both of them, on the left side of line C. For that reason, they are called one-sided angles, okay? Because of the fact that angles alpha and beta are located on the same side, that is to say they are located both on the left side of line C, they are defined one-sided angles. And the second question is why they are defined as interior angles. Actually, they are defined as interior angles because of the fact that both of them are located inside the structure of lines A, C, and B. They are inside this structure of lines A, C, and B. For that reason, they are defined as interior angles. Okay, so angles alpha and beta are defined as one-sided interior angles. Again, they are interior angles because both of them are located in the left side of line C. In relation to line C, they are both located in the left side of line C. For that reason, they are defined as one-sided angles. And because of the fact that they are both located inside the structure of lines A, C, and B, they are defined as interior angles. Okay, and we actually have second types of interior angles. Those are one-sided interior angles, and we also have one-sided exterior angles. If we have lines A and B, this is line A, and this is line B. If line C intersects those two lines, A and B, actually line C intersects line A at this point, while line C intersects line B at this point, then here angles alpha and beta are defined as one-sided exterior angles. Okay, so I write it down. Angles alpha and beta are one-sided exterior angles. Angles alpha and beta are defined as one-sided exterior angles. Again, they are one-sided angles because of the fact that both of those angles are located from the left side of line C. So for that reason they are defined as one-sided angles because both of them located on the same side of line C. That is to say, both of them are located on the left side of line C, and they are exterior angles because of the fact that both of those two angles are located outside the structure of lines C, A and B. They are both located outside of this structure of lines C and A and B. Okay, because of the fact they are defined as exterior angles. Okay. And actually we have a rule, I will call it rule number 1. According to rule number 1, if the sum of the two one-sided angles alpha and beta is equal to 180 degrees, then line A is parallel to line B. Okay, if the sum of those two one-sided interior angles are equal to 180 degrees, then line A is parallel to line B, and if the sum of those two one-sided exterior angles is equal to 180 degrees, then line A is parallel to line B. So I'll write it down. Rule number 1 states that if the sum of the two one-sided angles, and it doesn't matter at all if they are interior or exterior, that rule applies to both of those two types. Okay, they can be interior or exterior. So if the sum of the one-sided angles equals to 180 degrees, then line A is parallel to line B. So I read rule number 1 again. Rule number 1 states that if the sum of the one-sided angles equals to 180 degrees, then line A is parallel to line B, and it doesn't matter at all if the one-sided angles are interior angles or exterior angles. It applies, this rule applies to both of them. So actually here those are one-sided interior angles. So if alpha plus beta, the sum of those two angles, equals to 180 degrees, then according to rule number 1, line A is parallel to line B. Again, if the sum of those two angles, alpha and beta, is equal to 180 degrees, then according to rule number 1, line A is parallel to line B. And the same rule applies also to one-sided interior angles. If the sum of those two angles, alpha plus beta, equals to 180 degrees, then line A is parallel to line B. According to rule number 1. And also, as I've already said, that if the sum of those two one-sided interior angles equals to 180 degrees, then according to rule number 1, line A is parallel to line B. Okay? So we actually can implement rule number 1 in our circle, because angle ADC is a right angle, it equals to 90 degrees, and also angle BCD is also right angle, and it equals to 90 degrees. And those two right angles are one-sided interior angles. You can view line segment AD as line A, line segment BC as line B, and line segment EC as line C. So those two angles are defined as one-sided interior angles, and the sum of those two angles equals to 180 degrees. Therefore, according to rule number 1, line segment AD is parallel to line segment BC. So I will write it down. Angle ADC equals to 90 degrees. And angle BCD, this angle BCD, this angle also equals to 90 degrees, and actually the sum of those two angles are 90 degrees plus 90 degrees equals to 180 degrees. And I will emphasize the fact that those two angles are defined as one-sided interior angles. Okay, I write here that those two angles are defined as one-sided interior angles. And we know that the sum of those two angles is equal to 180 degrees. Therefore, according to rule number 1, line segment AD is parallel to line segment BC. So I will read again the things that I wrote. Angle ADC equals to 90 degrees. This angle is a right angle, it equals to 90 degrees. And angle BCD also equals to 90 degrees. And the sum of those two angles is 90 degrees plus 90 degrees is equal to 180 degrees. And those two angles are defined as one-sided internal angles. Again, because you can view line segment AD as line A. Okay, you can view line segment AD as line A, line segment BC as line B, and line segment DC that intersects those two line segments as line C. So those two angles are defined as one-sided interior angles. So therefore, and we know that the sum of those two angles equals to 180 degrees. Therefore, according to rule number 1, rule number 1 states that if the sum of the one-sided angles equals to 180 degrees, then line A is parallel to line B. If the sum of those two angles equals to 180 degrees, alpha plus beta equals to 180 degrees, then line A is parallel to line B. Okay? So according to rule number 1, we know that the sum of those two angles equal to 180 degrees. Therefore, line segment AD is parallel to line segment BC. According to number 1, line segment ID is parallel to line segment BC. Okay. So in the next step, we will connect together points A and C by a straight line. Okay, we connected together points A and C by a straight line, and we will also connect together points D and B by a straight line. And we will define the intersection point between line segment DB and AC is point O. Again, point O is defined as the intersection point between line segment AC and line segment DB. Okay, and in the next step, we will focus on triangles POC and triangles AOD. Okay, I will print it in the green color. We'll focus on those two green triangles, triangle POC and triangle AOD. Okay, and in addition, we will define the term vertex angles. What are vertex angles? Actually, if we have two lines, line A and line B, that are intersecting each other, this is line A, and this is line B. Those two lines, line A and line B, are intersecting each other, and the intersection point is this point. They are actually creating four angles. This is angle number 1, this is angle number 2, this is angle number 3, and this is angle number 4. Okay. So when two lines are intersecting each other, then they, at the intersection point they create 4 angles. 1, 2, 3, 4. Actually, angles 1 and 3 are defined as vertex angles, and according to the new rule, rule number 2, they are equal to each other. So I write it down. Angles 1 and 3 are defined as vertex angles, and according to the rule, to the new rule, rule number 2, they are equal to each other. Angle 1 equals to angle 3 according to rule, new rule, rule 2. Okay, I will read the things that I wrote. Angles 1 and 3 are defined as vertex angles, and according to rule number 2, they are equal to each other. So those two angles are defined as vertex angles, and according to rule number 2, angle 1 equals to angle 3. And also angle 2 and 4 are defined as vertex angles, and according to the same rule, rule number 2, they are also equal to each other. So angles 2 and 4 are also vertex angles, and according to the same rule, rule number 2, they are equal to each other. Okay, angles 2 and 4 are also vertex angles, and according to rule number 2, they also are equal to each other. Okay, so those two angles in the red color, angles 2 and 4, are also defined as vertex angles, and according to rule number 2, they are also equal to each other. So I will write down rule number 2. According to rule number 2, as I've already said, vertex angles are equal to each other. I will read again rule number 2. Rule number 2 states that vertex angles are equal to each other. So we actually have two pairs of vertex angles. Angles 1 and 3 are the first pair of vertex angles that equals to each other, and also the second pair of vertex angles are angles 2 and 4, and they're also equal to each other. So I will draw them separately in order to emphasize the issue. We have two lines that are intersecting each other. Line A intersects with line B. Okay, we have two lines that are intersecting each other. This is the intersection point. So they are actually creating two pairs of vertex angles. The first pair of vertex angles are those two angles, alpha and beta. They are vertex angles. Angles alpha and beta are vertex angles. Okay, and according to rule number 2, they are equal to each other. Those angles alpha and beta are the first pair of vertex angles that are equal to each other according to rule number 2, and the second pair of vertex angles that are equal to each other so actually those angles alpha and beta are the second pairs of vertex angles that are equal to each other according to rule number 2. Okay, so those angles alpha and beta are the second pair of vertex angles that are equal to each other according to rule number 2, while those angles alpha and beta are the first pair of vertex angles that are equal to each other according to rule number 2. Okay? So actually in our circle we can implement this rule number 2 in our circle, because angle AOD and angle BOC are those two angles are defined as vertex angles, and according to rule number 2 they are equal to each other. Okay, so I write it down. angle AOC equals to angle BOC because of the fact that those two angles are vertex angles. And according to rule number 2, they are equal to each other. Okay, angle AOC equals to angle BOC. Those two angles are equal to each other because of the fact that those two angles are vertex angles, and according to rule number 2, vertex angles are equal to each other, so those two angles are equal to each other. In the next step, we will define the term alternating angles. What are alternating angles? So actually, if we have two lines, line A and line B, and we have line C that intersects those two lines A and B. Again, we have two lines, line A and line B, and also we have line C that intersects line A at this point, and line C intersects line B at this point. Actually, in this situation, angles alpha and beta are defined as, those two angles alpha and beta are defined as alternating interior angles. Okay, or interior alternating angles. So write it down. Angles alpha and beta are defined as interior alternating angles. Okay, angles alpha and beta are defined as interior alternating angles. First of all, why are angles alpha and beta are alternating angles? The answer to this question is because of the fact that they are located in different sides of line C. They are defined as alternating angles. That is to say, angle alpha is located in the left side of line C, while angle beta is located in the right side of line C. For that reason, because of the fact that those two angles are located on different sides on different sides of line C, they are defined alternating angles. And also they are defined as interior angles. Why are they defined as interior angles? The answer to this question is that because of the fact that they are located inside the structure of lines A, C, and B, inside this structure, they are defined interior angles. Okay, so in total the angles alpha and beta are defined as interior alternating angles. Okay, they are interior angles because they are inside the structure of lines, line A, C, and B. They are inside this structure, for that reason they are interior angles. And they are alternating angles because they are located on different sides of line C. While angle alpha is located in the left side of line C, angle beta is located in the right side of line C. For that reason they are defined as alternating angles. Okay, and we also have the other type of alternating angles, the exterior alternating angles. Actually, if we have two lines, line A and line B, and we have line C that intersects those two lines, line A and line B. Okay, we have two lines, line A and line B, and we have line C that intersects line A at this point, and line C intersects line B at this point. Then angles alpha and beta are defined as exterior alternating angles. Those two angles, alpha and beta, are defined as exterior alternating angles. So I write it down. Angles alpha and beta are defined as exterior alternating angles. Again, why angles alpha and beta are alternating angles? The answer to this question is simply because of the fact that they are located on different sides of line C. While angle alpha is located on the left side of line C, angle beta is located on the right side of line C. For that reason, they are defined as alternating angles. And why are angles alpha and beta exterior angles? The answer to this question is very simple. because of the fact that those two angles are located outside of this structure. They are located outside of the structure of lines C, A, and B, outside of this structure of lines C, A, and B. They are located outside of this structure. For that reason, they are defined as exterior angles. Okay? So, actually, let me repeat again. We have those two types of alternating angles. Those angles are interior alternating angles, and those two angles are exterior alternating angles. And we actually have a rule for alternating angles, and it applies both to interior alternating angles and exterior alternating angles. Rule number 3 states that alternating angles and it doesn't matter at all if they are interior or exterior. It applies to both of them. Alternating angles between parallel lines are equal to each other. So I'll read rule number 3 again. Rule number 3 states that alternating angles, and it doesn't matter at all if they are interior or exterior, it applies to both of them. Alternating angles between parallel lines are equal to each other. So actually, in this drawing, if we know that line A is parallel to line B, if A is parallel to B, then according to rule number 3, angle alpha equals to angle beta. Okay? Again, if line A is parallel to line B, then according to rule number 3, angle alpha equals to angle beta. Those two angles are equal to each other. And we have also the same rule on interior alternating angles. If we know that line A is parallel to line B, okay, then according to rule number 3, angle alpha equals to angle beta. Okay, so according to rule number 4, alternating angles between parallel lines are equal to each other, and it doesn't matter at all if they are interior or exterior. The same rule applies to both of them. Those angles are interior angles and alternating interior angles, and if line A is parallel to line B, then angle alpha equals to angle beta, and those angles are exterior angles, exterior alternating angles, and if line A is parallel to line B, angle alpha equals to angle beta according to rule number 3. So it applies to both those two types of angles, interior and exterior. Whenever line A is parallel to line B, it doesn't matter at all if they are interior angles or exterior angles, they will be equal to each other. That is to say, alpha equals to beta if line A is parallel to line B. Okay, so now we will return to our original drawing, and we will focus on those two green triangles. So in triangle BOC, the big green triangle, and triangle AOC, the green small triangle, we have already proved that those two angles are equal to each other because they are vertex angles, and according to rule number 2, vertex angles are equal to each other. So angle AOD equals to angle BOC. Angle AOD is equal to angle BOC. Okay, those two angles are equal to each other. Okay, angle AOD equals to angle BOC according to rule number 2 that states that vertex angles are equal to each other. Okay, those two angles are vertex angles, and according to rule number 2, vertex angles are equal to each other. And also angle DAO, this angle is equal to angle BCO. to this angle. Okay, so those two angles are equal to each other because of the fact that those two angles are alternating angles. They are located in different sides of line segment AC. They are located on different sides of line segment AC, while angle BCO is located in the left side of line segment AC. Angle DAO is located in the right side of line segment AC. For that reason, they are defined as alternating angles. And according to rule number 3, alternating angles between parallel line or parallel line segments are equal to each other. We have already proved that AD is parallel to BC according to rule number 1. Those two line segments are parallel to each other, and we have two angles between those parallel line segments. So according to rule number 3, they are equal to each other because rule number 3 states that alternating angles between parallel lines are equal to each other. So angle DAO equals to angle BCO. Those two angles are equal to each other because of the fact that they are alternating angles. Those two angles are alternating angles, and they are located between parallel line segments. Line segment AD is parallel to line segment BC. So according to rule number 3, alternating angles between parallel lines are equal to each other. Okay, for that reason they are equal to each other. Okay, those two angles are equal to each other, or in other words, angle DAO is equal to angle BCO because they are alternating angles and they are located between parallel lines. Line segment AD is parallel to line segment BC. Therefore, according to rule number 3 that states that alternating angles between parallel lines are equal to each other, they are equal to each other. Okay, so angle DAO equals to angle BCO according to rule number 3. And also angle CBO or OBC, this angle equals to angle ADO, to this angle. Okay, so I will write it down. Angle CBO equals this angle equals to angle ADO because those two angles are alternating angles. Why they are alternating angles? Because they are located on different sides of line segment DB. While angle ADO is located on the right side of line segment DB, angle CBO is located in the left side of line segment DB. So For that reason, they are defined alternating angles, and they are located also between parallel lines, that is to say, line segment AD is parallel to line segment BC, so they are alternating angles that are located between parallel lines. Therefore, according to rule number 3, they are equal to each other. Okay? So, angle CBO equals to angle ADO. Because they are alternating angles. And they are located between parallel lines. Therefore, according to rule number 3, they are equal to each other. Okay, so angle CBO equals to angle ADO. Those two angles are equal to each other because of the fact that they are alternating angles, and they are located between parallel lines. Line segment AD is parallel to line segment BC. Therefore, according to rule number 3, they are equal to each other. So, we actually proved that three angles, all the three angles in this green big triangle are equal to three angles of this green small triangle, because we proved that angle BOC equals to angle AOC. Those two angles are equal to each other, and we also proved that angle DAO equals to angle BCO. Those two angles are equal to each other, and we also proved that angle CBO equals to angle ADO. Those two angles are equal to each other. So three angles of this triangle are equal to three angles of this triangle. So we actually proved that triangle CBO is similar to triangle ADO. Okay, we proved that triangle, the big green triangle CBO, is similar to the small green triangle, triangle ADO, according to the rule that of angle, angle, angle. Okay, we proved that triangle CBO, the big green triangle, is similar to triangle ADO, because we proved that three angles of the big green triangle are equal to three angles of the small green triangle. According to the rule of AAA, angle, 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 when you prove that three angles of one triangle are equal to three angles of the other triangle, then you actually prove that those two triangles are similar to each other. Okay, so actually, if we have two triangles, triangle ABC, we have two triangles, triangle ABC and triangle DEF, that are similar to each other, that is to say three angles of this big triangle are equal to three angles of this small triangle, then the following relationship between the sides of those two triangles is true. That's AB over DE equals to BC over EF equals to AC over DF. So this equality is true between those two similar triangles. That is to say AB over DE equals to BC over EF equals to AC over DF. Again, AB over DE equals to BC over EF equals to AC over DF. Okay? So in our drawing, we have the following relationship between those two similar triangles. OB over OD equals to OC over OA equals to BC over AD. Again, OB over OD equals to OC over OA equals to BC over AD. So this equality is true because of the fact that those two green triangles are similar to each other. Okay? The equality between the sides of those two similar triangles are OB over OD equals to DC over OA equals to BC over AD. But we know that BC equals to 8 units, it is given us in the question, and AD equals to 4 units. 4 units, so we can write here that BC equals to 8 units and AD equals to 4 units, so 8 over 4 equals to 2. Okay, so actually you have the equality that OB over OD equals to 2. Okay, OB over OD equals to 2. So we can write it separately. If we multiply this equality by OD, we will get that OB equals 2 times OD. Okay, OB equals 2 times OD. OB equals 2 times OD. So OB equals 2 times OD. So actually, if we define OD as A, then OB equals 2 times OD. OB equals 2 times A. Okay? Because OB equals 2 times OD, and if OD equals to A, then OB equals 2 times A. And we also can derive this equality that states that OC over OC over OA equals to 2. Okay, we can write it separately. Okay, the second equality, OC over OA equals to 2. We can multiply this equality by OA, and we will get that OC equals 2 times OA. Okay, OC equals 2 times OA. Okay, we got this equality that OC equals 2 times OA. So OC equals 2 times OA. So if we define that OA equals to B, then OC equals 2 times OA. So if OA is B, then OC equals 2 times B. Okay? OC equals 2 times OA. So if OA is B, then OC equals 2 times B. Okay? So in the next step we will find the values of A and B, and we'll focus actually angle ADC equals to 90 degrees. This angle is 90 degrees. It is given us in the question. Angle ADC equals to 90 degrees. Therefore, triangle ADC is a right triangle. So, in any right triangle, we can implement the Pythagorean theorem that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to the sum of the squares of the perpendiculars equals to AD square plus DC square. Okay, in the right triangle ADC, we implemented the Pythagorean theorem that states that the square of the hypotenuse equals to the sum of the square of the perpendiculars. The square of the hypotenuse is AC square equals to the sum of the squares of the perpendiculars equals to AD square plus DC square. Okay, now AC, line segment AC equals to OA plus OC. AC equals to AO plus OC, okay? But AO equals to B and OC equals to 2B. So in total AC equals to B plus 2B. That is to say AC equals to 3B. And AC square is 3B square equals to AD square. AD equals to 4, so AD square is 4 square plus DC square. DC equals to 6 units, so DC square is 6 square. So in total we got that 3b square equals to 4 square plus 6 square. 4 square is 16 and 6 square is 36. So I write it down. We got that 3b square equals to 16 plus 36. 16 plus 36 is 52. I write it down. So we got that 3b square equals to 52. Now we will take a root out of this equality. We will get that 3b equals to the root of 52. We took a root out of this equality. We got that 3b equals the root of 52. 52 equals to 13 times 4. And we also know that the root of a times b equals to root a times root b. So we can also split the root of 52 to root 13 times root 4. So we got that 3b equals to root 4 times root 13. The root of 4 is 2, so I write it down. So we got that 3b equals 2 times root 13. We will divide this equality by 3 and we will get the value of b. So we divided this equality by 3 and we got that b equals to 2 over 3 times root 13, and if b equals to 2 over 3 times root 13, then 2 times b equals to 4 over 3 times root 13. Okay, so I will write it here that b equals to 2 over 3 times root 13, while 2 times b equals to 4 over 3 times root 13. Okay, and we will repeat on the same process on this right triangle, we know that triangle angle BCD equals to 90 degrees. It is given us in the question. Angle BCD equals to 90 degrees. It is a right angle. Therefore, triangle BCD is a right triangle. So, in the right triangle BCD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars according to the Pythagorean theorem. The square of the hypotenuse is dB squared equals to the sum of the squares of the perpendiculars equals to DC squared plus BC squared. Okay, according to the Pythagorean theorem, in the right triangle BCD, the square of the hypotenuse, that is to say dB squared, equals to the sum of the squares of the perpendiculars equals to DC squared plus BC squared. Okay, what is the value of dB? dB equals to dO plus OB. And dO equals to A and OB equals to 2A. So in total dB equals to A plus 2A, that is to say dB equals to 3A. And dB squared equals to 3A squared equals to DC squared. DC equals to 6, so DC squared is 6 squared. Plus BC squared. BC equals to 8 units, so BC squared is 8 squared. Okay, so in total we got that 3 times A squared equals to 6 squared plus 8 squared. 6 squared is 36 and 8 squared is 64. Okay, so I write it down. So we got that 3 times A squared equals to 36 plus 64. 36 plus 64 is 100, so I write it down. So we got that 3A squared equals to 100. Now we will take a root out of this equality. Actually, the root of 100 is 10, so I write it down. So we took a root out of this equality. We got that 3A equals to the root of 100, and the root of 100 is 10, so we got that 3A equals to 10. We'll divide this equality by 3 and we will get the value of A. So we divided this equality by 3. We got that A equals to 10 over 3 units, while A equals to 20 over 3 units. So we can write here that A equals to 10 over 3 units, while 2 times A equals to 20 over 3 units. Okay, so actually we got all the values of all the line segments in this circle. I will copy this drawing without A and B because we already know the values of A and B. I will only write down the values of A and 2A, of B and 2B without A and B. Okay. EO is 10 over 3 units. OB is 20 over 3 units. OA is 2 over 3 times root 13. While OC is 4 over 3 times root 13. Units. 4 over 3 times root 13 units. Okay. In the next step, we will extend line segment AC until it touches the circle at point P. Okay, so we extended line segment AC until it touches the circle at point P. P is the point of contact between the circle and chord AP. Again, P is the point of contact between the circle and chord AP. Okay, so we created new line segment CP, and we will find the value of line segment CP according to a new rule number 4. Okay. Actually, rule number 4 states that if two chords are intersecting each other, for example, chord AB intersects with chord CD, and the point of intersection is point O. So chord AB intersects with chord CD at point O. So in this situation, the following equality is true: that AO times OB equals to CO times DO. Okay. Again, AO times OB equals to CO times OD. So if two lines are intersecting each other, that is to say line AB intersects with line chord AB intersects with chord DC at point O. Point O is the point of intersection between those two chords. Then the following equality is true, that OA times OB equals to CO times OD. Okay, OA times OB equals to CO times OD. So I will write down rule number 4. According to rule number 4, if two chords that is to say chord AB and CD are intersecting each other at point O, again, point O is the point of intersection between chord AB and chord CD. Then the following equality is true. AO times OB equals to CO times OD. So I will read rule number 4 again. If two chords, that is to say chord AB and chord CD, are intersecting each other at point O, point O is the point of intersection, then the following equality is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we actually can implement rule number 4 in our circle, because in our circle we have chord AP intersects with chord DB, at point O. Again, point O is the point of intersection between chord AP and chord DB. Therefore, according to rule number 4, AO times OP AO times OP equals to DO times OB. Again, according to rule number 4, because we have two chords, chord AP that intersects with chord DB, then according to rule number 4, AO times OP equals to DO times OB. Okay, so actually AO equals to 2 over 3 times root 13 OP equals to OC plus CP all equals to DO. DO is 10 over 3 units times OB. OB is 20 over 3 units. So, in total we got that 2 over 3 times root 13 equals to OP, but OP equals to OC plus CP. OP equals to OC plus CP. DO equals to 10 over 3, while BO equals to 20 over 3. Okay? What is OC plus CP? OC equals to 4 over 3 times root 13, and CP is the missing line segment. Okay? So we have 2 over 3 times root 13. OC is 4 over 3 times root 13. CP is the missing line segment, so we'll leave it as it is. CP and 10 times 20 is 200. So in total we got that 2 over 3 times root 13 times 4 over 3 times root 13 plus CP equals to 200 over 3 times 3. Here we have 3 in the denominator of this side of the equation, and we have 3 in the denominator of the other side of the equation, so 3 can be cancelled. So total we got that So after 3 is cancelled in the denominator, what is left is 2 times root 13 times 4 over 3 times root 13 plus CP equals to 200 over 3. Now we will open the brackets here, this side of the equation. We have root 13 times root 13 equals to 13, and 2 times 4 is 8. So I write it down. So we got here that 2 times 4 is 8 and root 13 times root 13 is 13. So in total we got here that 8 times 13 over 3 plus 10 times 2 times root 13 times CP equals to 200 over 3. 8 times 13 is 104, so I will write it down. So we got that 104 over 3 plus 2 times root 13 times CP equals to 200 over 3. We will subtract from this equality 104 over 3. We subtracted 104 over 3 from this equality. Here 104 over 3 minus 104 over 3 is 0. So we left only with 2 times root 13 times CP. And here 200 over 3 minus 103. 104 over 3 is 203 over minus 104 over 3. We take a common factor 3 here. We will get that 200 minus 4 equals to 96. So we got that 2 times root 14 times CP equals to 96 over 3. 96 over 3 is 32, so I write it down. So we got that 2 times root 14 times CP equals to 32. We'll divide this equality by 2. So we divided this equality by 2. We got that root 13 times CP equals to 16. We will divide this equality by root 13 and we will get the value of CP. So we divided this equality by root 13 and we got that the value of Cp is 16 over root 13 units. Okay, so we can write here that the value of Cp equals to 16 over root 13 units. Okay, in the next step we will extend line segment DC until it touches the circle at point Q. Again, we extended line segment DC until it touches the circle at point Q. Point Q is the point of contact between the circle and chord DQ, and we will find the value of CQ according to the fourth rule. Chord DQ intersects with chord AP at point C. Again, C is the point of intersection between chord AP and chord DQ. Therefore, according to rule number 4, DC times CQ equals to AC times CP. I'll read again the principle I wrote. Chord DQ intersects with chord AP at point C. Chord DQ intersects with chord AP at point C. C is the point of intersection between chord AP and DQ. Therefore, according to rule number 4, DC times CQ equals to AC times CP. Again, DC times CQ equals to AC times CP. Okay? And DC equals to 6 units. CQ is the line segment that is missing, so we leave it as it is. Equals to AC equals to AO plus OC, and AO equals to 2 over 3 times root 13, and OC equals to 4 over 3 times root 13, so in total AC equals to 6 over 3 times root 13. AC times CP. CP equals to 16 over root 13 units. Okay, so in total we got that 6 times CQ equals to 6 over 3 times root 13 times 16 over root 13. 6 over 3 is 2, and we also have root 13 in the numerator, and we have also root 13 in the denominator, so root 13 is cancelled. Okay, so in total we will get that 6 CQ equals to 2 times 16. Okay, 6 CQ equals 2 times 16. Because 6 over 3 is 2 and root 13 is cancelled, in total we got that we left only with 2 times 16. 2 times 16 is 32, so I write it down. We got that 6 CQ equals to 32. We will divide this equality by 6 in order to get out the value of CQ. So we divided this equality by 6 and we got that CQ equals to 13 over 6, but here we can divide the numerator and the denominator by 2. Okay, so we get that 32 over 2 is 16, while 6 over 2 is 3. So in total we got that CQ equals to 16 over 3 units. Okay. So CQ equals to 16 over 3 units. So in the next step we will extend line segment CB until it touches the circle at point R. We will extend line segment BC until it touches the circle at point R. Point R is the point of contact between the circle and chord RB. And we will find the value of RC, the new line segment that was created, by the fourth rule. Actually, chord DQ intersects with chord RB, at point C. Again, chord DQ intersects with chord RB at point C. Point C is the point of intersection between chord RB and DQ. Therefore, according to rule number 4, DC times CQ equals to BC times RC. Again, chord DQ intersects with chord RB at point C. Therefore, according to rule number 4, DC times CQ equals to BC times RC. Okay, so I read what I wrote again. Chord DQ intersects with chord RB at point C. Chord DQ intersects with chord RB at point C. Therefore, according to rule number 4, DC times CQ equals to RB times RC. Okay, so DC equals to 6 units and CQ equals to 16 over 3 units. While BC equals to 8 units and RC is the missing line segments. So in total we got that 6 times 16 over 3 equals to 8 times RC. 6 over 3 is 2, so I write it down. So we got that 2 times 16 equals to 8 RC. 2 times 16 is 32, so I write it down. Okay, we got that 32 equals to 8 RC. We'll divide this equality by 8 in order to get the value of RC. So 32 over 8 is 4, so we got that RC equals to 4 units. Okay, RC equals to 4 units. Now we have all the values of the line segments inside the circle, and the only missing thing is the radius of this circle, and we find the radius of this circle according to rule number 5. Actually, rule number 5 states that if we have two chords, chord AB, that intersects with chord CD at point O at 90 degrees, So if chord AB intersects with chord CD at 90 degrees at point O, then the following equality is true. That 4 times the radius squared, when R is the radius of this circle, equals to AO square plus BO square plus CO square plus OD square. Okay, so I will write down rule number 5. So rule number 5 states that if two chords that is to say chord A, B and C, D are intersecting each other at 90 degrees at point O, then the following equality is true, that 4 times the radius squared equals to AO square plus BO square plus CO square plus EO square. So I will read rule number 5 again. If two chords, chord AB and chord CD, are intersecting each other at 90 degrees, so at point O, so if chord AB intersects with chord AD at point O at 90 degrees, then the following equality is true. That 4 times R squared, when R is the radius of the circle, equals to AO square plus BO square plus CO square plus OD square. Okay? So we can implement rule number 5 in our circle, because we actually have chord DQ. Actually, first of all, we know that angle BCD equals to 90 degrees. Actually, all the angles at point C, all the 4 angles are right angles equal to 90 degrees. So, actually, chord DQ intersects with chord RB at 90 degrees. This angle is 90 degrees. All the angles at point C are 90 degrees. At point C, therefore, according to rule number 5, four times r squared when r is the radius of this circle equals to dc squared plus cq squared plus bc squared plus rc squared. So I'll read again the things that I wrote. Angle BCD equals to 90 degrees. This angle BCD, this angle is 90 degrees, is a right angle. And the chord DQ intersects with chord RB at 90 degrees. Chord DQ intersects with chord RB at 90 degrees. All the angles at point C are right angles. Therefore, according to rule number 5, 4 times r squared when r is the radius of this circle equals to dc squared plus cq squared plus bc squared plus rc squared. Again, 4 times r squared equals to dc squared plus cq squared plus bc squared plus rc squared. Okay, so actually 4 times r squared equals to dc equals to 6 units, so dc squared is 36 plus cq is 16 over 3 is 5 1/3, and 5 cq squared is 5 1/3 square is 28.444 plus bc square. bc equals to 8, so 8 square is 64 plus rc square. rc equals to 4, so 4 square is 16. So in total we got that 4r square equals to 36 plus 28.444 plus 64 plus 16. 36 plus 64 is 100, and 100 plus 16 is 116. 116 plus 28.444 equals to 144.444. Okay, so we actually got that 4 times r squared equals to 144.444. So we got that 4 times the radius square equals to 144.444. We'll divide this equality by 4 in order to find out the value of r squared. So we divided this equality by 4 and we got that r squared equals to 36.111. We know that the area of any circle equals to pi times the radius squared. That is the formula for the area of any circle in the world. It is pi times the radius squared. So the area of our circle will be equal, A is the area, equals to pi times r squared, but r squared equals to 36.111, so we can substitute r squared by 36.111 because it equals to r square. Okay, so we get 36.111 square units. Okay, so the area of the circle is 36.11 times pi square unit. So in terms of numbers, the area of the circle is 113.45 square units. Okay, I'll check that I'm not wrong. Okay, so we got that the area of this circle equals to 113.45 square units. Again, the area of this circle equals to 113.45 square units. So that is the answer to our question. Now I will summarize the lecture. Actually, we wanted to find out the area of this circle. We know that inside the circle we have a shape. Inside the shape we have two angles that equals to 90 degrees. This angle is 90 degrees and this angle is also 90 degrees. And side AD of the shape equals to 4 units, side DC of this shape equals to 6 units, and side BC of this shape equals to 8 units, and we want to find out the value or the area of this circle. Okay, and the first theorem that we must define before we will solve the question is the theorem of one-sided angles. Okay, what are one-sided angles? Actually, one-sided angles are defined as if we have lines A and B and line C that intersects line A and B, line C intersects line A at this point and line C intersects line B at this point. Actually, angles alpha and beta are defined as one-sided angles, while our angles alpha and beta are one-sided angles because they are located from the same side of line C. They both located on the right side of line C. For that reason, they are defined as one-sided angles. And why are they defined as interior angles? Because they are inside the structure of lines A, C, and B. They are inside this structure. For that reason, they are defined as interior angles. Okay, therefore they are defined as interior angles. So these angles are one-sided interior angles. And we have also the one-sided exterior angles. Why are those angles are one-sided angles? Because both of them are located on the same side of line C, the red line C. Both of them are located on the right side of line C. For that reason, they are defined as one-sided angles. And why are they exterior angles? Because angles alpha and beta are located outside of this structure, outside of lines C, A, and B. For that reason, they are defined as exterior angles. So those angles are one-sided exterior angles, and those angles are one-sided interior angles. And we have a rule number 1, that states that if the sum of the one-sided angles equals to 180 degrees, then line A is parallel to line B. And it doesn't matter at all if they are interior angles or exterior angles. It applies to both of them. If the sum of angles alpha plus beta equals to 180 degrees, then line A is parallel to line B. Okay? And also here, if the sum of angles alpha and beta equals to 180 degrees, then line A is parallel to line B. Okay? So we actually implemented rule number 1 in our circle, because in our circle we have this angle ADC that equals to 90 degrees, and also we have angle PCD that also equals to 90 degrees, and the sum of those two angles is 180 degrees, because 90 degrees plus 90 degrees equals to 180 degrees, and those two angles are defined as one-sided interior angles. They are interior angles because they are in the structure of ADCB, inside this structure, and they are one-sided angles because they are located from the downside of line segment DC. Okay, they are down of at the downside of line segment DC. So they are both on the downside of line segment DC. For that reason, they are one-sided angles. So we can view it like this. Both of those two angles are located, both those two angles are located in the left side of line segment TC. Okay, we look at line segment DC, both those two angles are located in the left side of line segment DC. For that reason, they are one-sided angles. So those two one-sided interior angles, the sum of those two angles is 180 degrees. So according to rule number 1, line segment AD is parallel to line segment BC. Okay, we have here two angles that are one-sided interior angles, and the sum of them is 100 equals to 180 degrees. For that reason, according to rule number 1, line segment AD is parallel to line segment BC. Okay. In the next step, we define the term vertex angles. Whenever you have two lines, line A and line B, that are intersecting each other, this is the point of intersection between line A and line B. We create two pairs of angles. The first pair is angles 1 and 3 are defined as vertex angles, and according to rule number 2 they are equal to each other. And the second pair of angles, of vertex angles, are angles 2 and 4 that are defined as vertex angles, and according to rule number 2 they are equal to each other. Okay, so actually rule number 2 states that vertex angles are equal to each other. So actually we have two types of vertex angles. As I've already told you, we have two pairs of vertex angles whenever two lines intersecting each other. So those two angles are defined as vertex angles, and according to rule number 2 they are equal to each other. And those two angles are the second pair of vertex angles, and according to rule number 2 they are also equal to each other. Okay, so that is the definition and rule of vertex angles. And in our circle, we actually connected together points D and B by a straight line, and we are also connected together points A and C by a straight line. We call to the intersection point between line segment DC and DB and AC at point O. And here we created two triangles. The green triangles we relate to the green triangles. In those two green triangles, angle BOC equals to angle AOC. According to rule number 2, actually they are vertex angles, and according to rule number 2, vertex angles are equal to each other. Okay, and then we define the term alternating angles. Here we have line A and line B and line C that intersects those two lines. The intersection between line C and line A is at this point, while the intersection between line C and line B is at this point. And actually those two angles, alpha and beta, are defined as alternating angles. Why are they alternating angles? Because of the fact that they are located on different sides of line C. While angle beta is the left, angle alpha is in the right side of line C, angle beta is in the left side of line C, so they are in different sides of line C. For that reason they are defined as alternating angles. and they are also interior angles because they are inside the structure of lines A, B, and C. They are inside that structure, and therefore they are interior angles. And we have also the second types of alternating angles. Those angles are exterior alternating angles. Again, they are alternating angles because they are located on different sides of line C. Angle alpha is in the right side of line C, while angle beta is in the left side of line C. For that reason, they are defined as alternating angles, and they are exterior angles because of the fact that they are outside the structure of lines A, B, and C. They are outside of this structure. They are located outside of this structure. For that reason, they are defined as exterior angles. And we have rule number 3 that states that alternating angles, no matter if they are interior or exterior angles, between parallel lines are equal to each other. So if we know that line A is parallel to line B, then we can deduce that angle of alpha is equal to angle beta. If line A is parallel to line B, then angle alpha equals to angle beta. And also here, if line A is parallel to line B, then angle alpha equals to angle beta. Okay, so that is rule number 3. And in these two right triangles, we proved that those two angles are equal to each other because they are vertex angles, and according to rule number 2, vertex angles are equal to each other. And also angle DAO equals to angle BCO. Those two angles are equal to each other. Why? Because they are alternating angles that are located between parallel line segments. Line segment AD is parallel to line segment BC, so alternating angles between parallel lines are equal to each other, so that for that reason they are equal to each other. And also we have those two angles that are also alternating angles, and they are located between parallel line segments. Line segment AD is parallel to line segment BC, and according to rule number 3, alternating angles between parallel lines are equal to each other. For that reason they are equal to each other. So we actually proved that 3 angles of this triangle equals to 3 angles to this triangle, because we proved that those two angles are equal to each other because they are vertex angles, and those two angles are equals to each other because they are alternating angles between parallel lines. And we also, those two angles are equal to each other, again because of the same reason, because they are alternating angles between parallel line segments, therefore they are equal to each other. So we proved that 3 angles of this triangle equals to 3 angles of this triangle. So we actually proved that the big green triangle is similar to the small green triangle. And whenever we have two triangles that are similar to each other, we have the following relationship between the sides of those two triangles. If triangle ABC is similar to triangle EDF, then AB over DE equals to BC over EF equals to AC over DF. So we implemented this equality in our circle. We can say that OB over OD equals to OC over OA equals to BC equals to BC over AD. Okay? And we got from this equality that OB equals to 2 times OD and OC equals to 2 times OA. Okay? And so we have here OA, if OA equals to B, then OC equals to 2B, and if OD equals to A, then OB equals to 2A, according to the relationship that we found. And we actually know that angle ADC is a right angle, therefore triangle ADC is a right triangle, so we can implement the Pythagorean theorem on the right triangle ADC. On the right triangle ADC, AC square equals to AD square plus DC square, and we know that AC equals to 3B, AD equals to 4 units, and DC equals to 6 units. So we can put the data inside the Pythagorean equation, and we found that found out that B equals to 2 over 3 times root 13, while 2 times B equals to 4 over 3 times root 13. And then we know that angle BCD, this angle is a right angle, therefore triangle BCD is a right triangle, so we can again implement the Pythagorean theorem in the right triangle BCD. The Pythagorean theorem states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars, and we know that BD equals to 3A, BC equals to 8 units, and DC equals to 6 units. The only missing variable is A. We put the data inside the Pythagorean equation, and we found out that A equals to 2 over 3 units, while 2 times A equals to 20 over 3 units. Okay, and then actually we copied this drawing here. We found A and B because we know the values of A and B, and we extended line segment C until it touches the circle at point P, and we found out the value of CP according to the fourth rule. The fourth rule states that if two chords are intersecting each other at point O, then the following equality is true, that we have two chords A, B, and C that are intersecting each other at point C, then the following rule is true, that AO over OB equals to CO over OD. Okay, so we implemented this rule in our circle because we have chord AP that intersects with chord DB at point O, so therefore we can implement rule number 4 here. We can say that AO times OP equals to DO times OB, and the only missing line segment is CP. We put the data inside this equation, and we found out that the value of CP is 16 over 13 units. Okay, and then we extended line segment DC until it touches the circle at point Q, and then we calculated the value of line segment CQ according to the fourth rule. Actually, chord DQ intersects with chord AP at point C. Therefore, according to rule number 4, DC times CQ DC times CQ equals to AC times CP, and okay, DC times CQ equals to AC times CQ, and the only missing variable is CQ. We put the data inside this equality, and we found out that CQ equals to 16 over 3 units. Okay, CQ equals to 16 over 3 units. Then we extended line segment BC until it touches the circle at point R, and we found out the value of RC, the line segment RC, according to the fourth rule. Chord DQ, this chord intersects with chord RB at point C. So according to the rule number 4, DC times CQ equals to BC times RC. The only missing line segment is RC. Okay, we have this equality. DC times CQ equals to BC times RC. RC is the only missing line segment. We put the data inside this equality and we found out that RC equals to 4 units. Okay, so we have all the values of all the line segments inside this circle, and the only missing thing is the radius of this circle, and we found the radius of this circle according to rule number 5. Rule number 5 states that if two chords, chord AB intersects with chord CD at 90 degrees at point O, then the following equality is true, that 4 times R squared, when R is the radius of the circle, equals to AO squared plus OB squared plus CO squared plus DO squared. Okay, we can implement rule number 5 in our circle because we know that first of all, angle BCD, this angle is a right angle. It is given us in the question. Actually, all the angles around point C is 90 degrees, and actually chord DQ intersects with chord RB at 90 degrees. All the angles here are 90 degrees. The point of intersection between chord DQ and RB is point C. Therefore, according to rule number 5, 4 times R squared equals to DC squared plus CQ squared plus BC squared plus RC squared. And we know all the values of all the line segments here. According to rule number 5, 4 times R squared equals to DC squared plus CQ squared plus BC squared plus RC squared. So we know the values of all the line segments here. We put the data inside this equality, and we found out that the radius square of this circle equals to 36.111, and the area of any circle in the world equals to pi times the radius squared. So the area of this circle will be pi times R squared. We found out that R squared equals to 36.111, so we can substitute R squared here in the formula for the area of a circle by 36.111. So we substituted R squared by 36.111, and we found out that the area of this circle equals to pi times 36.111 square units, or in terms of numbers, the area of this circle equals to 113.45 square units. Again, the area of this circle equals to 113.45 square units. Okay? Thank you very much.